Energy can be thought of as the capacity to do work, or equally, the capacity to bring about change. The study of energy, or thermodynamics, is an important discipline in biology. In thermodynamics, two laws governing energy are utilized. The first law of thermodynamics states that energy is never lost or gained, but is only transformed. For example, in a steam engine, energy locked up in the chemical bonds of coal is transformed into heat energy and mechanical energy. There is no loss of energy in this process, but energy is transformed from a more ordered, concentrated form, such as the chemical bonds of coal, to a less ordered, more dispersed form, such as heat. The second law of thermodynamics states that entropy, which is a measure of the amount of disorder in a system, always increases with a transfer of energy. In other words, when energy is produced, matter changes from a more ordered state to one of less order. When a lump of coal is burning, ashes are produced, and hot air disperses into the atmosphere. In the steam engine at the left, energy locked up in chemical bonds of the coal is transformed into heat energy and mechanical energy. The system obeys the laws of thermodynamics since there's no loss of energy, only transformation, and entropy is increasing with the transfer of energy to air. Energy input is necessary in order to store away energy. For example, energy is required to build up a more complex molecule, in this case glycogen, from simpler molecules, in this case the individual glucose units. Why? Because a large glycogen molecule is a more complex, ordered chemical object than the individual glucose molecules it's made of. The flip side of this is that the breakdown of a larger molecule, such as glycogen, into its component parts does not require a net input of energy. In fact, some energy will be released in such a reaction. ATP, short for adenosine triphosphate, is life's most important energy transfer molecule. It stores energy in the form of chemical bonds between its phosphate groups. When the bond between the second and outermost phosphate group is broken, the outermost phosphate separates from ATP and energy is released. This separation transforms ATP into adenosine diphosphate, or ADP, and a molecule of inorganic phosphate. ADP then goes on to pick up another phosphate group, an energy-consuming reaction, becoming ATP again. The ATP is then capable of providing energy for yet another reaction. The shuttling from ATP to ADP and back takes place constantly in cells.